Now let us start with a short review of complex numbers. A complex number can be represented using two real numbers, x and y. In this form, z is equal to x plus jy. Here, x is the real part and y is the imaginary part. The same complex number can also be represented by its magnitude and its argument. In this form, z is equal to r times exponential of j theta. Here, r is the distance from the origin and theta is the angle measured from the real axis. On the complex plane, the horizontal axis is the real axis and the vertical axis is the imaginary axis. A single complex number is represented as one point, or equivalently, as one vector on this plane. The angle theta is called the argument of z. Therefore, we sometimes write it as arg of z. This representation is useful when we consider multiplication of complex numbers. Suppose that we have two complex numbers, z sub 1 and z sub 2. If we write them using their real and imaginary parts, the product becomes x sub 1, x sub 2 minus y sub 1, y sub 2, plus j times x sub 1, y sub 2, plus x sub 2, y sub 1. This expression is correct, but the meaning is not very clear. On the other hand, if we write the two complex numbers using magnitude and argument, the calculation becomes simple. Let z sub 1 be r sub 1 times exponential of j theta sub 1. Let z sub 2 be r sub 2 times exponential of j theta sub 2. Then the product z sub 1 z sub 2 is equal to r sub 1 r sub 2 times exponential of j times theta sub 1 plus theta sub 2. This tells us a very important geometrical meaning. The magnitude of the product is the product of the two magnitudes. The argument of the product is the sum of the two arguments. In other words, when complex numbers are multiplied, their lengths are multiplied, and their angles are added. This way of thinking is especially important in electronic and communication engineering. For example, consider impedance. Impedance represents the relationship between voltage and current. We write this relationship as V equals Zi. Here, V is voltage, I is current, and Z is impedance. All of these quantities are represented as complex numbers. Therefore, the equation V equals Zi has two meanings. First, for the magnitudes, the magnitude of V is equal to the magnitude of Z times the magnitude of I. This means that the ratio of the voltage amplitude to the current amplitude is the magnitude of the impedance. Second, for the arguments, the argument of V is equal to the argument of Z plus the argument of I. This means that the phase of the voltage is shifted from the phase of the current by the argument of the impedance. Therefore, impedance expresses two relationships between voltage and current using one complex number. One relationship is the amplitude ratio. The other relationship is the phase difference. If we draw voltage and current as sinusoidal functions of time, we can see these two relationships visually. The ratio of amplitude corresponds to the magnitude of the impedance. The horizontal shift or phase difference corresponds to the argument of the impedance. Thus, a complex impedance compactly describes both amplitude and phase in a single number.